Hello, my name is Pedro Ramalhet, and I'm here to talk about efficient algorithms for persistent transactional memory. This is joint work with Andrea Correia and Pascal Felber at University of Neuchâtel. There are four ways to do durable transactions. The first one is undo log, and in undo log what you do is you have a persistent log and you keep there the original data before you actually modify it. And this is the case of techniques like PMEM OBJ in PMDK. At the end of the transaction, you clear the log, and that's it. You can commit safely. In read log, you also have a persistent log, but it works the other way around. First, you do the modifications on the persistent log, and at the end of the transaction, you reapply those modifications over the original data. All of this has to be made with fences at the right place. Examples of this technique are Mnemosine and OneFile. Then there's copy on write, sometimes called shadow copy, and in shadow copy you usually have a pointer or a logical pointer, and when you want to do a modification you create an entire replica of your data with these modifications, and then you do a single pointer swap with flushes and fences to indicate that the new data is the next one. And on shadow data is kind of similar like copy and write, but it's not the same thing because you keep two replicas the whole time and you keep them up to date. First, you apply the modifications on one of the data of the replicas, then you toggle the pointer, then you apply the modifications on the other replica. The next time you toggle the pointer in the opposite direction. Now let's talk about Trinity, which is the algorithm that we show on the paper. Trinity utilizes a kind of shadow data durability where two replicas of the data are kept in the same cache line. We call them main and back. We also keep metadata, which is just a sequence number, 64-bit sequence number. There's also one single word which we call PSEC, which is global metadata, and it's just a sequence number of the last committed transaction. Stores are interposed as we go along on the transaction, and we keep the old value on the back. We copy the old value to the back, and we write directly in place on the main the new value. So as you can see, when we did a equals 1, b equals 2, we wrote directly into the place for main. And we updated in the end the transaction number to be the new transaction number, which is 32. At commit time, we increment the PSEC, which is the global transaction number, to 33 to indicate that all transactions whose sequence is lower than 33 are committed and durable. Notice that the ordering of the stores is guaranteed by the PCSO model, so no fences are issued until the end of the transaction. We developed a second technique which we call Trinity VR, where a volatile replica of the main data is kept in volatile memory, in this case DRAM, but it can also be in persistent memory, but it's volatile. So what this means is that as we execute the transaction, loads are done in place, and we can have variable-sized data types. So that means strings can be executed just in one go without having to be intersected by the back and the main as metadata. So what this means is that when we're writing to DRAM, and when we're reading from DRAM, and it's only at commit time when we end the transaction that the Trinity protocol is executed, and this data is copied from DRAM to persistent memory, updating the sequence numbers at each cache line, and finally the PSEC. Now let's talk about how to merge concurrency with this algorithm. When combining the volatile replica with the TL2 concurrency control, we keep the main components of TL2 in DRAM, in volatile memory. That means the array of blocks, the global clock, the write set, and the read set, those are kept in volatile memory. One extra change is needed in persistent memory for the Trinity algorithm, where we have one PSEC per thread instead of having a single PSEC. So we need an array of sequences with one entry per thread. The load interposing and the start interposing of the TL2 concurrency control are just the same as the original, except we use an undo approach with write-through execution. At commit time, we follow a protocol very close to the original TL2. We check if the transaction is read-only by looking if the write set is empty. We do read set validation, and only after the read set has been validated, we know that from a concurrency point of view, this transaction has committed. So now, and only now, are we going to replicate those writes on persistent memory. Up until then, it's all been done, all modifications have been done in volatile memory. We then increment the global clock, we do the durable commit using the Trinity protocol, and then we release the locks. The important point here is that first we do the durable commit, and only then we make the transaction visible to other threads. So durability first while grabbing all the locks, and then we release the locks. In the abort, remember, all the operations have been done solely on DRAM, so we can simply revert those using the typical TL2 approach and restart execution by calling a long jump. In case of a system crash, what we do is we execute the Trinity recovery protocol, reverting the last transaction if it's not committed, and then we copy the entire PM data into the volatile region, and we can start executing transactions from that point on. Using the Trinity VR PTM, we created the Trinity DB with two variants, one where the concurrency control is given by TL2, and the other where the concurrency control is flat combining. Those are the green and blue lines in this plot. These are write-intensive workloads in the DB benchmarks, which are benchmarks created by LevelDB and later by RobsDB, also used by PMEM-KV. The override has the best scalability of them all because it has no allocations being done for reinsertions. Whenever the key is found, the value is just overwritten in place, so no further allocations. And allocations are costly because that means more writes. More writes means more flushes in the transaction. On pure random reads, flat combining wins because of the lower overhead. It just has to take one read lock and then execute its entire transaction with no extra cost in synchronization. It's very hard to beat that. And it's doing all of that on DRAM, which gives it a lot more performance than the other techniques. But on the read while writing, a single thread is doing insertions into the database in parallel, and that causes the performance to drop immediately because it's a global lock. For TL2, this doesn't happen. The performance is nearly the same because the TL2 concurrency control allows read-only transactions to execute in parallel with write transactions as long as they are disjoint. The main insights of this work is that reducing the number of flashes to persistent memory is vital to have high-performance, durable transactions. And Trinity and Quadra algorithms do exactly that. They trade higher memory usage to have better throughput. And another insight is if you have enough DRAM available, then combining it with PM will yield the best performance possible. And concurrency-wise, well, if you have workloads that are mostly disjoint, then TL2 is the way to go. If you have things where the workload is really very serializable, like everybody's writing on a queue, then you're better off with something like flat combining. And RPTMs are implemented as a single C++ header with a bit more than 1,000 lines of code. And, you know, less code means less bugs. And a fast and scalable persistent transactional memory makes it easy to create a fast and scalable key value store. Thank you.